Keeper 5.2, derivatives of parametric equations. All right, so we have two derivative formulas. The second one is the one that we use most often because that's dy dx. So this is the one that we like to use. But you can have dx dy depending on your situation. But let me focus on the second one. The second one says dy dx equals dy over dt over dx over dt, and that's our formula that we're going to use, provided that dx over dt does not equal 0, because then we would have an undefined situation. All right, so example 1 says find the tangent lines to the tangent line or lines to the parametric curve at 0, 4, given by x equals t to the 5th minus 4t cubed and y equals t squared. So the first thing I'm going to find the derivative, because I know in order to get the tangent line, I need the derivative or the slope of the tangent line. So I'm going to find the derivative of the parametric function. So remember, your derivative is dy over dx equals dy over dt over dx over dt. And so dy over dt is 2t, and dx over dt is 5t to the 4th minus 12t squared. Simplifying that out, canceling out a t, I'm left with the derivative of 2 over 5t cubed minus 12t. All right, so now that I have that derivative, I want to find the value of t that yields 0, 4. Okay, because 0, 4 is the point xy, and I really want to know what t is so I can find the derivative of dy dx at t equals whatever number. So basically what I'm going to do is I'm going to start with the easier equation, which will be y equals t squared. I know that y equals 4, so that means t must equal plus or minus 2. Well, if t equals plus or minus 2, we want to check to see if one of those work or both of those work in the x equation. So if I plug in 2 into the x equation, I get 0, which is what I want x to be. And if I plug in negative 2, I also get 0, which I want x to be. So that means both t equals 2 and t equals negative 2 satisfy the two equations. That tells me that I'm going to end up with two tangent lines. All right. So next I want to solve for dy dx at both of my t values. So I'm going to do dy dx such that t equals 2. When I plug in 2 for t, I get 1/8. And then I'm going to do dy dx at t equals negative 2. And when I plug that in, I get negative 1/8. So now to write out my equations of my tangent lines, I'm going to start with the t equals 2 one. And so I'm going to get y minus 4 equals 1/8 x minus 0, or 1/8 x. I can also write that if I wanted to as y equals 1/8 x plus 4. And then using the other equation, I would have y minus 4 equals negative 1/8 x minus 0, or negative 1/8 x. And again, I can rewrite that if I wanted to. I don't have to. But I can rewrite that as y equals negative 1/8 x plus 4. All right, we can also use these derivatives to find horizontal tangents and vertical tangents. If I want to find a horizontal tangent, I want my numerator of the derivative to equal 0. So I want dy dt to equal 0. Again, provided that dx dt doesn't equal 0. And then if I want a vertical tangent, I want my denominator to equal 0, because I want it where basically where the derivative doesn't exist. And so I would do dx dt equals 0. Again, provided that dy dt does not also equal 0. All right, so again, they want, in this example, they want us to find the horizontal and vertical tangents. They give us x equals t cubed minus 3t, and then y equals 3t squared minus 9. So let's start with the horizontal tangents. So for horizontal tangents, we need to solve dy dt equals 0. dy dt in this case is going to be 6t. We want to set that equal to 0, and we set t equals 0. Well, if t equals 0, then x equals 0, and y equals negative 9. So the place where I have a horizontal tangent is going to be 0, negative 9. Next, I want to find my vertical tangents. And so I want to do dx dt equals 0. And so dx dt is 3t squared minus 3. If I set that equal to 0, I get t squared equals 1, or t equals plus or minus 1. Note that the t values for the horizontal and the vertical tangents are different, so I'm still good to go. If they were the same, then we would have a different situation. All right, so now I want to plug both of my t's into my equations. So I have x of 1 equals negative 2, y of 1 equals negative 6, x of negative 1 equals 2, and y of negative 1 equals negative 6. Therefore, my points of vertical tangents would be negative 2, negative 6, and 2, negative 6. All right, so now we have a formula for the second derivative of our parametric equations, and I might show you guys the proof for this in class, but basically your second derivative is the derivative of the first, or the derivative of the first derivative divided by dx dt. All right, so in this example, they want us to find the second derivative of the parametric equation. So the first thing I'm going to do is take my first derivative, which we found in example 1, to be 2 over 5t cubed minus 12t. And so to find my second derivative, I'm going to take the derivative of that, the derivative of the first derivative, which I have to use quotient rule. So I have low d high minus high d low over low low, all over my denominator down here is going to be all over dx dt again. So dx dt was 5t to the fourth minus 12t squared. So I have to divide it by that number again. All right, so when I simplify it, I get 24 minus 30t squared over 5t cubed minus 12t all squared times 5t to the fourth minus 12t squared. If I factor out a t in this second expression on the bottom, if I factor out a t, I'll be left with 24 minus 30t squared over t times 5t cubed minus 12t all to the third power. All right, so example 4, it says determine the values of t for which the equation is concave up and concave down. We should know by now that if we need to find concavity, we have to find the second derivative. So I'm going to start by finding that second derivative. In order to do that, I must find the first derivative. Remember, the first derivative is dy dt over dx dt. So I have 7t to the 6th plus 5t to the 4th over negative 2t. All right, then for the second derivative, I'm going to use quotient rule of the first derivative divided by dx dt again, so divided by an additional negative 2t. When I simplify that, I get negative 35t to the 6th minus 15t to the 4th over t cubed, or simplified some more, I get 35t cubed plus 15t over 4. All right, so now that I have that derivative, I want to set it equal to 0 to find where I have points of inflection. All right, so when I set it equal to 0, I get 35t squared plus 14 all times t equals 0. Setting each one of those factors equal to 0, I get t equals 0. And then the other one, I get an imaginary number. So t equals 0 is the only place I'm concerned about. So I'm going to take that t equals 0, I'm going to plug it on the number line, and I'm going to plug in values to the left and right of it into my derivative. And I notice that when I plug in negative numbers, I get negative numbers out. And when I plug in positive numbers, I get positive numbers out. Which tells me that my function is concave up when t is greater than 0 and concave down when t is less than 0.